Hello, my name is One. I'm going to be guiding you through the fantastic dynamics of the water distribution in Grand Teton National Park, focusing on the Snake River and its evolving characteristics. So, when we're trying to understand river type and its characteristics, the Snake River is a good example of a meandering river, characterized by its curving bends. These bends are shaped by natural processes of erosion and deposition. Erosion occurs on the outer banks where water flows fastest, while sediment deposition happens on the inner banks where velocity decreases. Together, these processes shape the river, and I've kind of detailed where these processes happen on this picture. Looking at the future of the Oxbow Lake, we can see that the interplay between erosion and deposition over time, the Snake River may evolve into an oxbow lake as it becomes increasingly isolated from the main channel. This transition is driven by sedimentation and a natural cutoff process, a hallmark of a meandering river. Looking at evidence for processes occurring in the Snake River, the image I've chosen shows an abandoned curve of the river downstream. The formation of such feature can often be attributed to reduced water flow, sediment buildup, and channel cutoff events. These scarves serve to show historic markers of the river's ever-changing path. So the image I've chosen is highlighted here by some of the history the lake has to offer. Looking at the Snake River panorama, we notice a steep cut bank on the outer bank. This indicates active erosion. Additionally, as sediments are transported and vegetation patterns shift, we observe how the river continues to reshape its surroundings. Like at some point, this could have been full of vegetation, but due to erosion, this is now barren and it's created a steep drop off. So, describing the plains of the Snake River. It is a broad and fertile area extending all the way to the base of the Teton Mountains. Here, sediment deposition plays a critical role, creating an alluvial plain rich in nutrients, which process exemplifies the long-term dynamic history of river systems contributing to the park's biodiversity. So this is some ways the river helps maintain good health. So, looking for evidence on if terraces are seen, it is difficult to tell based on the images gathered. This lack could be due to ongoing sediment deposition and minimal vertical incisions. Essentially, the river's energy is focused on horizontal expansion rather than cutting deeper into the bed. So based on the pictures I saw on Google Earth, I believe that the river is forming more like this rather than like this. So I do not think that terraces are present. So moving into finding some of my variables to look for our 50-year pattern, I'm going to show you how I found these graphs. So I started off on the USGS and I searched up Snake River, Wyoming, and I have chosen this particular location. It's called Snake River near Moran. So once I click that, I'm going to be able to see the discharge cubic feet per second, but it's only up to a week, and the same thing for the gauge height. So once I move over to the data and I click on annual statistics and I click for just the discharge, I'm going to put it for a whole year and then submit. This is the discharge in cubic feet per second, which is 704.7. And I can also see this in a different way on this site by going to the site page and selecting the gauge height for up to a year. And that is the gauge height for a year at the near Moran in Snake River. So, oh, moving forward, I'm going to talk about characteristics of the Snake River watershed. So we can see that the land use for this area is mainly evergreen forest and shrubs. So this is good because it's not going to have a lot of human-led pollution or much agriculture runoff from like excessive fertilizer use. And we can see that the soil is slow to infiltrate, but that's not too much of a concern because that's the natural state of the soil and it's not being impacted by man-made issues. So the stream quality should be very natural and self-regulating because of the minimal interference of the human population in this area. So when I was trying to find my gauge size, I referenced this paper. I believe it's this one. I referenced this paper specifically. Oh, I think it's this table. Where's the table? Here we go. I specifically referenced this table, and if you look at my presentation, I used this number that's located in the Middle Rockies. And when I was finding the parameters and areas for my location, the near Moran is right before a dam. So I looked at the width before the dam, which was 74.49. And when I looked at the length, I measured it from the starting point of my width all the way up until there was a bit of a curve and it cuts off the straight flow. So that was 300.96. And then I also took into account the elevation of my location, as when we're trying to find the slope, we divide the elevation by the total length. So finding the sediment input, I referenced this paper, which helped me get my numbers for how to find the sediment input and based on location. So this is the math that I used once I started to find these different variables. For my bankful discharge, I had to convert it. And then my intermediacy, I was able to find that on the USGS. And what I basically did over here is I counted the amount of times that the average discharge was less than or greater than the number I got for my year total. And I used the grain sized with the paper referenced earlier, and I showed my channel width. And then after I converted my bankful discharge for my sediment, what I basically did is I got my total area of the watershed. I will show you. So I got the total area of the watershed and I got the area of the watershed. And I divided the area of the watershed by the total area, and then I got a variable of 0.492. So then I used this paper, which helped me use the average sediment delivery to water bodies. And when I multiplied those two, I got a number that I will present over here, which was 255,840,000. And that was how I found my sediment input. So once I added every single variable presented here inside of my Excel sheet and I clicked on calculate, this was the bed evolution I would see over the next 50 years. So we're specifically going to be looking at this line. So if we're looking at the implications of increased sediment size over the next 50 years, we are going to see impacts of aquatic habitats reducing quality and spawning grounds. This basically means when fish lay their eggs, they're more likely to get eroded and not being able to come to full fertilization because of the increased sediment size. It's going to be pushing everything a lot heavier. And the changes in stream morphology and channel stability include things like degradation and aggravation. So the finer part sediment sizes might be flowing more freely, but the larger ones are going to stay there, and that's going to impact the river over time because they're going to be too heavy. The water isn't going to be able to push them, and that's going to make the river become more standstill and have a decreased imbalance. So the sediment supply is also going to be impacted by erosion of upland areas. So here are my references. I used Google Earth. I used two different scientific papers, one for understanding my sediment input and the other was for calculating my grain size. I also used the USDA USGS National Dashboard and model my watershed. Thank you.